Picture a civilization so advanced that it could sense an earthquake before it struck, or redirect a raging river with nothing but stone and sheer ingenuity. Think about structures that have weathered not just centuries, but millennia, surviving disasters that would flatten modern cities. This isn't science fiction. This was reality for countless ancient societies, whose engineering secrets have been hiding in plain sight, waiting for us to listen. Today, we're pulling back the curtain on 29 breathtaking techniques developed by master builders from lost worlds, methods so sophisticated they almost feel like magic. From the earthquake-defying walls of the Incas to the ingenious flood control systems of Mohenjo-Daro, these ancient marvels weren't just impressive, they were lifelines. They allowed civilizations to thrive in some of the most hostile environments on Earth, turning disaster into opportunity and fear into resilience. What's even more astonishing is that many of these techniques are not just historical curiosities. They hold powerful, often overlooked lessons for today's engineers, architects, and city planners, especially as we face growing climate challenges and natural disasters of our own. So join us on a journey across time and continents as we explore how human creativity triumphed over nature's fury. We'll walk through storm-proof harbors, climb quake-resistant temples, and dive into subterranean water networks that outsmarted droughts. This is more than a history lesson. It's an invitation to see the past with new eyes and to rediscover a legacy of innovation that still whispers wisdom to those willing to listen. Picture standing at the ruins of Sacsayhuaman, the massive fortress overlooking the ancient Inca capital of Cusco. You run your hand over the stones, and your finger's trace seems so tight you cannot slip a piece of paper between them. These are not simple bricks, they are a sprawling, chaotic jigsaw puzzle of gigantic, irregularly shaped blocks, some weighing over 100 tons, all fitting together with impossible precision. Now imagine the ground begins to tremble. In a modern city, you'd hear the sickening crunch of concrete and the shatter of glass, but here something almost magical happens. The wall dances, the entire structure sways and shifts, the stones grating against one another, only to settle perfectly back into place once the earthquake passes. This is not luck. This is polygonal masonry, one of the most sophisticated seismic-resistant building techniques ever conceived. The genius of Inca stonemasonry lies in its beautiful simplicity. They used no mortar, no metal clamps, no modern engineering diagrams. Instead, they achieved an almost supernatural level of precision through painstaking craftsmanship. Using harder stones and sand to grind and shape each block, they created these complex, interlocking joints. The result is a wall where every stone is surrounded by multiple neighbors, all holding each other in a state of perfect tension and compression. It's a unified system, a single, flexible entity. During an earthquake, the energy from the seismic waves is not concentrated into a few weak points, as it is in a rigid, mortared wall. Instead, that destructive energy is dissipated. It's transformed into harmless kinetic energy as the stones slide and shift against each other, absorbing the shock and preventing a catastrophic collapse. What's truly humbling is that modern engineers, with all our technology and advanced materials, are still trying to fully decode and replicate this ancient wisdom. In laboratories and computer models, they study the dynamics of these walls, confirming that the slight, controlled movement between the stones is the key to their resilience. It's a principle we now call a seismic design, and the Incas were mastering it centuries ago. They built for the specific challenges of their environment. The Andes is one of the most seismically active regions on the planet, and their solution was not to fight nature's power with brute strength, but to work with it, to design with flexibility and intelligence. This ancient method stands today not just as a relic, but as a timeless lesson in resilience, showing us that sometimes the most advanced solution is also the most elegantly simple. Now shift your gaze from the mountains of Peru to the shimmering coast of Italy. Picture a bustling Roman harbor 2,000 years ago. Ships heavy with grain and marble from across the empire glide into a port that seems to defy the very sea it's built upon. The waves crash, the salt spray flies, but the concrete piers and breakwaters stand unyielding. Fast forward to today. A modern concrete seawall might show signs of crumbling decay after just a few decades in that same salt water. But these ancient Roman structures, many are not only still standing but are actually stronger now than when they were first poured. The secret to this seemingly impossible durability lies in a revolutionary recipe, one that modern scientists have only recently begun to fully decipher. The Romans didn't just build with concrete, they engineered a living material. Their key ingredient was a specific type of volcanic ash known as pozzolana, which they sourced from deposits around the Bay of Naples. They would mix this fine ash with lime and small chunks of rock or brick, and then something truly counterintuitive, they used seawater to bind it all together. To any modern builder, this sounds like a recipe for disaster. Saltwater is the enemy of modern concrete, causing the steel reinforcements inside to rust and expand, leading to cracks and eventual failure. But Roman concrete had no steel. Its strength came from a complex chemical reaction between the pozzolana, the lime, and the seawater itself. When seawater percolates through the concrete, it reacts with the volcanic ash and lime to form a rare, incredibly sturdy mineral called aluminous tobermorite. This crystal acts like a reinforcing fiber, weaving through the material and actually filling in any tiny cracks that begin to form. It's a self-healing material. The very thing that destroys our modern structures, seawater, is what continuously repairs and strengthens the ancient Roman ones. This mastery allowed the Romans to undertake engineering projects of breathtaking scale and audacity. The massive dome of the Pantheon, still the world's largest unreinforced concrete dome nearly 2 millennia after it was built, is a testament to their material strength and stability. Their aqueducts marching across valleys for miles carried life-giving water to millions, and their harbors, like Portus Cossonus, created calm, deep water sanctuaries from stormy coastlines, enabling the Roman navy and merchant fleets to project power and wealth across the Mediterranean. They built with a confidence we struggle to match today because they understood their material on an almost instinctual level. For centuries, the precise recipe was lost to history, a forgotten trick of a fallen empire. It's only through advanced tools like electron microscopes and X-ray microdiffraction that modern researchers have been able to peer into the molecular structure of these ancient samples and finally understand the magic the Romans created by hand. This isn't just a historical curiosity. It's an active field of research, with scientists now experimenting with modern versions of Roman concrete, hoping to create more durable and sustainable marine structures, from seawalls to tidal energy generators, that can heal themselves and last for centuries, not just decades. While the Incas tamed earthquakes with shifting stone, and the Romans forged a concrete that grew stronger in the sea, another civilization was solving a different kind of natural threat entirely. Journey now to the sun-scorched plains between the Tigris and Euphrates rivers, the legendary cradle of civilization known as Mesopotamia. Here, the danger wasn't the trembling earth, but the sky itself. Life in this region was a bargain with two extremes, punishing droughts that could wither crops and starve cities, and then, without warning, devastating flash floods that could roar down from the northern highlands, obliterating everything in their path. It was against this volatile backdrop that the Mesopotamians erected their most iconic structures, the massive, stepped temples known as ziggurats, and in doing so, they engineered them to be far more than just religious symbols. They were brilliant, multi-layered fortresses against the deluge. The great ziggurat of Ur, dedicated to the moon god Nana, is a perfect example of this ancient hydrological genius. At first glance, it appears as a solid mountain of mud brick, a towering stairway to the heavens, but its true secret lies hidden beneath the surface. The core of the ziggurat was actually constructed from sun-dried mud bricks, a material readily available but highly vulnerable to water. A single heavy rain could have turned this entire monumental core into a shapeless, collapsing mound of mud. So the builders devised a protective shell. They encased the entire structure in a thick, waterproof skin of baked bricks, fired in kilns to become hard and impervious. Then they took their defense a step further, using naturally occurring bitumen, a tar-like petroleum substance, as a powerful sealant, slathering it between the baked bricks to create a nearly impenetrable barrier against moisture. Yet, the real masterstroke was how they dealt with the water that inevitably pooled on the vast, flat surfaces of each tier during a downpour. Instead of letting it cascade down the sides and erode the sacred facade, they designed an intricate, hidden network of internal drainage channels. These carefully engineered conduits, woven through the brickwork like a secret vascular system, would silently gather the rainwater and channel it safely away from the vulnerable core, directing it out through strategically placed outlets far from the foundation. This prevented the water from seeping inward to weaken the structure or from collecting at the base to undermine it. The ziggurat wasn't just built to be admired, it was built to shed water, to stand firm while the tempest raged around it. This was integrated water management on a colossal scale, a testament to a society that understood its environment so intimately that it could literally build its prayers to withstand the very storms sent by the gods. Now consider a different kind of challenge, one not of construction but of pure, monumental logistics. Imagine a single block of red granite, taller than a 10-story building and weighing as much as 500 cars. This is an Egyptian obelisk, a needle of stone precision carved from a single piece of rock, meant to be transported hundreds of miles across desert and river to stand before a temple. The sheer scale of moving such an object seems impossible even with today's cranes and heavy transport vehicles. For the ancient Egyptians, it was a regular feat of engineering, and their solution was a masterclass in applying simple physics to an overwhelmingly complex problem. They didn't have the wheel in any form capable of handling such a load, so they turned to the ground itself, using friction not as an enemy to be defeated, but as a force to be cleverly manipulated. Their primary tool was the sledge, a massive wooden platform that distributed the obelisk's immense weight. But dragging a load of over 400 tons through sand would create impossible friction, digging the sledge into the ground and requiring a pulling force far beyond what any army of workers could provide. The Egyptian innovation was stunningly simple yet profoundly effective. They turned the desert into a slipway. As depicted in tomb paintings, teams of workers would walk ahead of the sledge, pouring water onto the sand directly in its path. This wasn't just to keep the dust down. The water saturated the sand, drastically reducing the friction coefficient. The grains of sand, when dry, pile up and create a plowing resistance, but when wet, they stick together through surface tension, creating a much smoother, firmer surface. In some cases, they may have used a slurry of wet clay for an even more effective lubricant. This simple act transformed the sand from a grabbing, shifting obstacle into a hard, slick track, reducing the pulling force required by as much as 50%. This method was about far more than just making the load easier to pull. It was about control and risk mitigation. Moving an obelisk was a perilous operation that could take months. A single mishap, a snapped rope, a cracked stone, a sudden shift in weight could mean the destruction of a decades-long project and the loss of countless lives. By dramatically reducing friction, they also reduced the sudden, jarring forces that could cause catastrophic failure. The movement became smoother, more predictable, and far safer. Teams of laborers, coordinated by overseers using drums or horns, could pull in a steady, synchronized rhythm, guiding the monument on its slow, deliberate journey to the Nile. There, it would be loaded onto a specially built, enormous barge for the final leg of its voyage. This incredible logistical operation, from quarry to temple, showcases a deep, practical understanding of physics that allowed them to achieve a smoothness of transport we would now associate with advanced machinery. They looked at the problem not in terms of the overwhelming weight they had to move, but in terms of the invisible forces they needed to manage, and they found a breathtakingly elegant solution hiding in plain sight: a few pots of water and the sand beneath their feet. But perhaps the most astonishing aspect of these ancient water highways was the human endeavor required to build them. The construction of a Kanat was a monumental task undertaken by specialized crews known as mukanis. These were not just laborers, they were highly skilled engineers, geologists, and surveyors who worked in incredibly dangerous conditions. Using nothing but hand tools like picks and hoes, and a specially designed leather bucket to remove spoil, teams would begin by sinking a mother well, often over 100 meters deep, to locate the water table. From there, they would begin the painstaking process of digging the gentle slope of the tunnel itself, backward from the intended outlet point. The true genius lay in the surveying. Using nothing more than simple sighting tools and an innate understanding of gravity, these ancient engineers had to maintain a perfect, consistent gradient, a drop of only 1 meter for every 1,000 meters of length, over distances that could stretch for miles. A single miscalculation could mean the tunnel would be too steep, causing erosive flooding, or too shallow, leaving the water stagnant and useless. Ventilation shafts were dug upward to the surface every 20 to 30 meters, not only providing crucial airflow for the workers, but also serving as guides to ensure the tunnel was being dug in a perfectly straight line. These shafts, visible as lines of craters marching across the desert landscape, became the silent signature of this incredible technology, a testament to a civilization that refused to be conquered by its environment and instead engineered a lifeline straight from the heart of the earth. While the Egyptians mastered the physics of moving mountains of stone, an inventor in ancient China was grappling with an invisible and far more unpredictable force, the very movement of the earth itself. In the year 132 AD, during the prosperous Han Dynasty, a brilliant polymath named Heng unveiled a device that must have seemed like something from mythology. It was a large, ornate bronze vessel, perhaps as tall as a man, adorned with 8 dragons, each gazing outward in a cardinal or intercardinal direction. At the base, directly beneath each serpent's head, sat 8 corresponding bronze frogs, their mouths open in anticipation. This magnificent object was not a ceremonial ornament. It was the world's first seismoscope, a machine designed to detect earthquakes from hundreds of miles away, and its operating principle was so elegant it borders on wizardry. The genius of Heng's invention lies in its beautiful mechanical simplicity. Inside the vessel, historians and engineers believe, was a delicately balanced inverted pendulum, a kind of weighted post that could swing freely. When seismic waves, those invisible pulses of energy that radiate from an earthquake's epicenter, traveled through the ground and reached the device, they would set this internal mechanism in motion. The pendulum would sway in the direction from which the waves originated. This motion would, in turn, trigger a clever lever system connected to the dragon facing that same direction. The dragon's jaw would clack open, and a heavy bronze ball held within would drop with a resonant clang directly into the waiting mouth of the frog below. The sound alone would have been an alarm, but the specific dragon that released its ball provided the critical intelligence. It pointed unerringly toward the source of the disaster. Imagine the scene in the Han capital of Luoyang, a quiet day with no tremors felt by anyone in the city. Suddenly, a loud clang echoes from the palace chamber housing the seismoscope. A ball has dropped from the dragon facing west. The court officials now have a life-saving piece of information. A major earthquake has struck somewhere to the west. They could immediately dispatch cavalry messengers and relief supplies in that precise direction, days before any slow-moving reports from devastated villages could possibly arrive. Historical records tell us this exact scenario played out. The court initially felt nothing and was skeptical of the device's warning, but days later, messengers arrived from a western province reporting a massive quake that had leveled cities hundreds of miles away. The seismoscope had not only detected the event but had accurately pinpointed its direction, proving its incredible utility. This was more than just a clever gadget. It represented a quantum leap in human thought. It marked a shift from a passive, reactive relationship with natural disasters to a proactive, scientific one. Heng understood that earthquakes were not the capricious acts of angry gods, but physical phenomena that followed predictable rules and could be measured. His device was founded on the core principles of modern seismology, the understanding that Earth vibrations travel in waves and that their point of origin can be triangulated. While our tools today are electronic and far more precise, the fundamental goal remains identical: to detect, locate, and respond. Heng's seismoscope stands as a powerful testament to the fact that true innovation isn't always about creating complexity, but about applying profound insight to create elegant simplicity, turning the invisible into something that can be seen, heard, and acted upon. Now, let's travel deep into the steamy rainforests of Central America, where the ancient Maya faced a paradox that would challenge any civilization. They lived in a region of abundant rainfall, yet they were constantly on the brink of water crisis. Unlike other great empires that grew around mighty rivers, the Maya heartland was built on a porous limestone bedrock, a geological sponge that swallowed rainwater almost as fast as it fell. For months, torrential downpours would flood the land, only to be followed by severe seasonal droughts where surface water vanished completely. Survival here wasn't about controlling floods, it was about capturing every precious drop and making it last. And at the great city of Tikal, they solved this puzzle with a breathtaking network of reservoirs that transformed the entire urban landscape into a giant water harvesting machine. The genius of Tikal's design is visible from the sky. The city's grand plazas and courtyards paved with plaster were not merely public spaces, they were engineered catchment basins. During the rainy season, these vast, impermeable surfaces sloped gently, channeling torrents of rainwater through a carefully designed system of canals and conduits directly into massive, lined reservoirs. But the Maya understood that water straight from the sky and off the streets wasn't yet fit to drink. So they incorporated a sophisticated purification process before a single drop entered the main storage tanks. The water would first flow into smaller, preliminary settling basins. Here, the heavy sediments, debris, and contaminants would naturally sink to the bottom, allowing clearer water to flow into the primary reservoirs. This simple yet effective method of sedimentation, a precursor to modern water treatment, ensured the stored water remained cleaner and far less likely to stagnate or become a breeding ground for waterborne diseases. What truly set the Maya apart was their holistic ecological vision. These reservoirs weren't hidden away on the city's outskirts. They were integrated into the very heart of Tikal, positioned centrally among the towering temples and royal palaces. This wasn't just a practical decision for easy access. It was a powerful statement of control and divine order. The rulers who managed this life-giving resource cemented their political and spiritual authority. The water system supported a population that may have reached 60,000 people at its peak, all living in a region with no permanent rivers. They even managed the surrounding forest as a vital part of the system, understanding that deforestation on the hillsides would lead to erosion that could silt up their precious reservoirs. This interconnected view of urban planning, hydrology, and ecology allowed Tikal to flourish for over 1,000 years, overcoming droughts that might have shattered a less ingenious society. Their reservoirs were more than just holes in the ground. They were the beating heart of the city, a testament to a civilization that didn't just build monuments to the gods, but engineered a symbiotic relationship with the very environment that sustained them. From the humid jungles of the Maya, we journey now to the heart of another empire, one defined not by water scarcity but by unprecedented urban density. Picture the city of Rome at the height of its power, a teeming metropolis of over 1 million souls. Its narrow, winding alleys are crammed with towering apartment blocks called insulae, made primarily of wood and vulnerable to the smallest spark. A single overturned oil lamp, a careless cooking fire, or a bolt of lightning could and did unleash an inferno capable of consuming entire neighborhoods in hours. After a series of catastrophic fires, most famously the Great Fire of Rome in 64 AD, the Romans did something remarkable. They didn't just improve their firefighting techniques, they fundamentally re-engineered their city from the ground up, pioneering a systematic approach to urban planning that turned a chaotic tinderbox into a more resilient and healthier metropolis. This was disaster mitigation through architecture and law. The most visible change was the radical redesign of the city's very skeleton. Where crooked, cramped pathways had once allowed flames to leap effortlessly from one rooftop to the next, the Romans now mandated wide, straight streets and open public squares. These new thoroughfares acted as natural fire breaks, creating gaps too wide for most flames to cross and providing clear access for the city's dedicated fire brigade, the Vigiles. This corps of 7,000 men, established by Emperor Augustus, was more than just bucket bearers. They were a professional night watch patrol equipped with pumps, hooks, and ballistae to create demolition lines. But the Romans understood that the best way to fight a fire was to prevent it from starting in the first place, or to stop it from having fuel. This led to one of history's first comprehensive building codes. New constructions, especially the multi-story insulae, were increasingly required to use fire-resistant materials. Walls were to be made of brick or concrete, and the use of wood for external balconies and facades was heavily restricted. They even began to use a form of double-wall construction with a gap filled with rubble, which acted as insulation, slowing the transfer of heat and giving inhabitants precious time to escape. Perhaps the most ingenious element of this system was its integration with another Roman marvel, the aqueduct network. These engineering wonders did more than supply bathhouses and private villas. They were the lifeblood of the city's fire defense. Public fountains, fed directly by the constant, gravity-powered flow of the aqueducts, were strategically placed throughout the city. These provided a never-ending, reliable water source for the Vigiles, who could tap into them with their siphon pumps. This eliminated the desperate, chaotic scramble to wells or the Tiber River that had doomed so many city blocks in the past. The wide streets allowed the vigiles to move their equipment quickly. The brick construction denied the fire its fuel, and the aqueducts provided the means to douse it. This holistic strategy transformed urban resilience, dramatically reducing the frequency and deadliness of major conflagrations. The legacy of this Roman innovation extends far beyond fire prevention. The same wide streets that slowed fires also improved sanitation and air circulation, reducing the spread of disease. The abundant public fountains provided clean drinking water, improving public health. This systematic approach to urban design, considering fire, water, health, and transportation as interconnected systems, became a blueprint for cities across the empire and echoes in the principles of modern urban planning. Building codes mandating fire-resistant materials, zoning laws that require open space, and municipal water systems designed with hydrants and emergency access in mind all find their roots in the pragmatic, life-saving reforms of ancient Rome. They demonstrated that a city is not just a collection of buildings, but a living organism, and to protect it from disaster, you must engineer its very veins and bones. While the Romans were redesigning their city above ground to combat fire, an even earlier civilization was mastering the art of urban survival far below the surface, in the unpredictable floodplains of the Indus Valley. Over 4,000 years ago, the great city of Mohenjo-Daro was a marvel of hydraulic engineering, a bustling metropolis where the greatest threat wasn't fire but water. Located in what is now Pakistan, this city faced the dual menace of torrential monsoon rains and the overflowing Indus River. Yet, instead of being constantly ravaged by floods and plagues, Mohenjo-Daro thrived for centuries, and its secret weapon was a hidden world of sanitation and control that wouldn't be matched for thousands of years. Walking through its streets, you wouldn't see grand pyramids or ziggurats first. You'd notice the quiet, elegant order of a city that had public health as its founding principle. The most astonishing feature was the city's underground vascular system, a comprehensive network of covered brick sewers that ran beneath every major street. Each house, from the smallest dwelling to the largest courtyard home, was connected to this main system through clay pipes and chutes. Wastewater from baths and latrines would flow into these street-side drains, which were meticulously covered with brick or stone slabs to contain odors and prevent debris from clogging them. But this was more than just a sewage system. It was a sophisticated flood management tool. During the intense monsoon season, these same channels would efficiently carry stormwater away from the city's streets and buildings, preventing the kind of catastrophic flooding that could paralyze a less prepared settlement. The entire city was gently sloped, using gravity to ensure a constant flow toward collection points outside the residential areas, a testament to incredibly precise urban surveying. This obsession with cleanliness and order extended to every corner of daily life. Houses were equipped with dedicated garbage chutes that emptied into large, sealed brick bins at street level, a form of municipal waste collection that kept refuse off the streets and away from disease-carrying pests. But the Indus Valley people understood that resilience wasn't just about managing water once it was in the city. It was about keeping it out of the most vital places in the first place. This is where their most prominent architectural feature comes into play, the massive mud brick citadel that loomed over the western side of the city. This raised acropolis, towering over 40 feet above the plain, was more than an administrative or religious center. It was a life raft. In the event of a severe flood, this elevated platform would become an island of safety, protecting the community's leaders, its sacred spaces, and its most critical food reserves from the rising waters. Those food reserves highlight another layer of their ingenuity. The Great Granary of Mohenjo-Daro was a massive structure built on a raised, ventilated platform. The design featured a double row of rectangular bays with air cavities beneath the floor. This clever architecture served a crucial dual purpose. The raised platform protected the precious stores of grain from ground moisture and minor flooding, while the sophisticated ventilation system allowed a continuous flow of air to circulate, preventing the buildup of heat and humidity that would lead to rot, mold, and spoilage. It was a climate-controlled warehouse from the Bronze Age, ensuring food security even in the dampest conditions. This holistic approach, combining street-level sanitation, elevated citadels, and intelligent storage, created a resilient ecosystem. They didn't just build structures, they built a system where waste was managed, water was controlled, and resources were protected, allowing a sophisticated urban culture to flourish for nearly a millennium in an environment that should have been overwhelmingly hostile to dense human settlement. Now, let's set sail from the orderly streets of Mohenjo-Daro into the choppy, war-torn waters of the Byzantine Empire, where survival often depended on a terrifying, almost supernatural weapon that seemed to bend the very laws of nature. Picture this: you are a sailor aboard an Arab warship in the 7th century, part of a massive fleet laying siege to the legendary city of Constantinople. Your ship closes in on the great sea walls, confident that victory is near. Suddenly, a strange tube emerges from a Byzantine dromon galley. There's a loud whoosh, and a stream of liquid fire arcs through the air. It hits the water near your ship, and the sea itself erupts into flames. This is not ordinary fire. It clings to the wooden hull, it sizzles on the waves, and nothing, not water, not sand, not frantic beating, can put it out. Panic erupts. This is Greek fire, the Byzantine Empire's most closely guarded secret, and one of history's most formidable psychological weapons. A masterpiece of ancient chemical engineering that turned the sea from a battlefield into a defensive moat of pure nightmare. The true terror of Greek fire, known to the Byzantines as sea fire or liquid fire, lay in its horrifying properties. Unlike any incendiary weapon before it, this concoction wasn't just flammable, it was persistently and defiantly so. Historical accounts describe it as a sticky, glutinous liquid that would adhere to whatever it touched: sails, hulls, and most horrifyingly, the sailors themselves. Water seemed to only feed its fury. Some theories suggest its composition created a chemical reaction that released oxygen, allowing it to burn even underwater. This meant that a ship, once hit, had almost no chance of survival. The only recourse was a desperate and often futile attempt to smother the flames with vinegar or sand, materials rarely on hand in the heat of a naval battle. But the horror didn't stop at its physical properties. The Byzantines deployed it with terrifying efficiency through a pressurized siphon, a bronze tube mounted on the prows of their ships that functioned like an ancient flamethrower. Operators, protected by a barrier of iron, could sweep this jet of fire across the water, creating a wall of flame that could engulf multiple ships at once. The sound alone, a thunderous roar accompanied by thick, black smoke, was enough to shatter enemy morale before the first drop even landed. What makes Greek fire a trick that defied natural disasters, however, goes beyond its use in warfare. It was the ultimate tool for controlling a chaotic environment. The sea is inherently unpredictable, with storms, waves, and currents that can scatter and destroy the most powerful fleets. For the Byzantines, whose entire empire was based around the capital of Constantinople and its vulnerable sea walls, a naval invasion was a natural disaster of the highest order. Greek fire effectively tamed that environment. It turned the water itself into an ally, a burning barrier that was impassable in any weather. Chronicles note it could be used effectively even in high winds and rain, conditions that would render any ordinary fire attack useless. This gave the Byzantines an unparalleled defensive advantage, allowing them to face down vastly larger fleets with a handful of ships equipped with these siphons. They didn't just have a weapon, they had a force of nature under their control. The most fascinating aspect of Greek fire is that its exact recipe died with the empire. To this day, its complete composition remains one of history's great unsolved mysteries, a secret so valuable that it was known only to a handful of individuals, perhaps even only one family within the Byzantine royal court. Modern chemists and historians have their theories, of course. The most plausible suggest a base of crude petroleum or naphtha, distilled from surface oil seeps around the Black Sea, mixed with resinous pine sap or gum to make it sticky, and possibly other ingredients like quicklime, which ignites on contact with water or saltpeter. But no modern reconstruction has perfectly matched the terrifying descriptions from ancient texts. This intentional obscurity was itself a brilliant strategic move. By making the weapon seem magical and invincible, the Byzantines amplified its psychological impact. Enemies didn't just fear the fire, they feared the unknown power behind it. This single invention, a product of unparalleled chemical ingenuity, is credited with saving Constantinople from multiple sieges over centuries, single-handedly preserving the heart of the Roman Empire in the East for hundreds of years longer than would have otherwise been possible. It stands as a powerful reminder that sometimes the greatest engineering tricks aren't just about physical structures, but about mastering the very elements to create a shield so formidable that its legend alone could deter disaster. After witnessing the Byzantine mastery of fire on the high seas, we now turn to a quieter, more intimate form of engineering, one that worked in perfect harmony with the Earth itself. Journey to the high desert mesas of the American Southwest, where the sun beats down with an unforgiving intensity in the summer and the winter nights plunge into a deep, bone-chilling freeze. Here, the ancestral Puebloans, often called the Anasazi, didn't just build shelters, they sculpted their homes directly into the living rock, creating communities like the breathtaking cliff palace at Mesa Verde that remain marvels of environmental adaptation. Their genius wasn't in grand monuments, but in creating a life of remarkable comfort and safety in one of North America's most climatically extreme regions, using nothing but stone, wood, and an intuitive understanding of the sun's path. The most obvious advantage of building under the massive, sweeping overhangs of canyon walls was immediate shelter from the elements. These great stone roofs provided a permanent shield from the punishing summer sun and the heavy snowfall of winter. But the Anasazi's architectural brilliance went far beyond this simple protection. They engineered their dwellings to become natural thermal regulators, achieving a stable, livable temperature year-round without any need for mechanical heating or cooling. The secret lay in their sophisticated use of passive solar principles, a concept we often think of as modern sustainable design. They positioned their multi-story structures strategically on south-facing cliffs. During the short, low-angled days of winter, the sun would arc across the northern sky, its rays penetrating deep into the recesses of the alcove, warming the dark stone walls of the dwellings. These walls would act as thermal mass, absorbing the sun's heat throughout the day, and then slowly releasing it back into the living spaces through the long, cold night, creating a natural and efficient heating system. Conversely, during the blistering summer months, the sun takes a much higher path directly overhead. The massive sandstone overhang now performed a perfect function, casting a deep, continuous shadow over the entire village like a giant awning. This kept the intense, direct solar radiation from ever hitting the dwellings, allowing the coolness of the stone and the canyon itself to maintain a pleasantly moderate temperature inside. They further enhanced this natural cooling with clever ventilation. The design often included small, strategically placed openings and the use of different levels within the complex. Warm air would naturally rise and escape through higher openings, drawing in cooler air from below in a continuous, gentle convection current that refreshed the living quarters without a single draft of wind feeling unpleasant. This wasn't just comfortable, it was a matter of survival, drastically reducing the physical strain on the body in a climate of extremes and preserving precious resources like water that would otherwise be needed for cooling. Their site selection also displayed a profound understanding of hydrology and disaster avoidance. These cliff dwellings were never built at the very bottom of the canyon, where sudden, violent flash floods after a distant thunderstorm could scour a settlement away in minutes. Instead, they were perched safely midway up the cliff face, high enough to be completely immune to any floodwaters, yet low enough to have reasonable access to the seeps and springs that emerged from the canyon walls and to the gardens they cultivated on the mesas above. The construction materials themselves were a lesson in localism and resilience. They used the sandstone blocks they quarried directly from the alcove floor, shaping them with harder stones and bonding them with a simple mud mortar. This meant their entire building supply was sourced on site, eliminating any complex logistics and creating structures that were, quite literally, of the same substance as their surroundings. This seamless integration is precisely why these dwellings have endured for over 7 centuries. They weren't placed upon the landscape, they were woven into it, a testament to a civilization that understood that the greatest trick to defying nature's harshness is not to fight it, but to listen to it and learn its rhythms. While the Anasazi carved their homes into sun-drenched cliffs to harness the desert's extremes, another group of settlers faced a completely opposite and in many ways more daunting challenge: the relentless, all-consuming cold of the Arctic. Imagine the world of a Norse Greenlander around the year 1000 AD. You've sailed west from Iceland, following the legendary Eric the Red to this new land he optimistically named Greenland. But the reality is a brutal, stark beauty. The summer is fleeting, a short burst of green that quickly surrenders to a winter so long and dark it feels eternal. The wind howls across the fjords with a force that can steal your breath, and the cold is a physical presence, a constant enemy that seeks any weakness in your shelter, any gap in your defenses. To survive here, the Norse couldn't just build houses, they had to forge fortresses of warmth. Their solution was a masterclass in insulation and thermal efficiency, a building technique so effective it allowed them to cling to life on the edge of the known world for centuries. The core of their design was a simple but powerful layering system, using the very materials the harsh landscape provided. They would construct a sturdy frame of driftwood or, if they were fortunate, scarce imported timber. But the true genius was in the walls. They built 2 parallel walls, an inner and an outer shell, using stones gathered from the rocky soil. This created a cavity, but instead of leaving it empty, they packed it densely with turf, cutting thick, heavy blocks of the dense, grassy topsoil. This turf was far more than just filler. It was a phenomenal natural insulator. Think of it as the Viking equivalent of modern fiberglass batting or foam board. The densely matted grass roots and soil created millions of tiny air pockets, and trapped air is one of the best barriers against heat transfer. This thick turf wall acted like a giant, earthen blanket wrapped around the entire structure, dramatically slowing the escape of precious warmth from inside while blocking the penetrating Arctic cold from getting in. Location was everything. They didn't place their longhouses proudly on open plains where they would be fully exposed to the elements. Instead, they nestled them into south-facing hillsides. This strategic positioning served multiple critical functions. The earth berm of the hill provided additional natural insulation on the north and west sides, the directions from which the most severe winds and weather typically came. It also offered a significant windbreak, forcing the frigid gusts to flow over the top of the structure rather than slamming directly into its walls. Furthermore, building into a slope helped with drainage, preventing melting snow and ice from pooling around the foundation and seeping inside. The entrance to these homes was often a long, tunnel-like passageway that dipped down before opening into the main room. This design feature, known as a turf tunnel, created a cold sink. Since cold air is heavier, it would settle in this low area of the tunnel, acting as a plug that prevented the warmer air inside the living quarters from escaping every time the door was opened. It was a simple, passive airlock system. Inside this well-insulated shell, life centered around the heart of the home, the long, central hearth. This wasn't just a fireplace for cooking, it was the primary heating system. The stone and turf construction was perfect for this. The materials had high thermal mass, meaning they absorbed heat from the fire slowly, and then released it back into the room gradually over many hours, long after the flames had died down to embers. This even, radiant heat prevented the wild temperature swings that would occur in a less substantial building, maintaining a stable, livable environment. The smoke would rise and slowly seep out through a hole in the roof, and the low ceilings helped keep the warmth at the level where people lived and slept. This combination of super-insulated walls, strategic location, and efficient heat retention allowed a single fire to provide comfort for a large family through the long polar night. This architectural resilience was put to the ultimate test starting in the 13th century with the onset of the Little Ice Age. As global temperatures cooled, the already marginal environment of Greenland became even harsher. Winters grew longer, sea ice increased, disrupting trade and navigation, and the growing season shortened. While many factors contributed to the eventual end of the Norse settlement, their innovative home construction was undoubtedly a key reason they managed to persist for as long as they did. Their stone and turf longhouses were a testament to human adaptability, proving that even in the most unforgiving climates, ingenuity could create a pocket of warmth against the cold, a defiant stand against the ice that, for a time, truly made a Greenland out of a glacier. Leaving behind the intimate, insulated homes of the Norse, we traveled to a scale of engineering so vast it reshaped an entire landscape and sustained a metropolis larger than any in the medieval world. In the humid, tropical heart of Cambodia, the Khmer Empire faced a climatic tyranny of its own, the brutal pendulum swing between deluge and drought. For half the year, the monsoon would arrive with a vengeance, dumping torrential rains that swelled rivers and flooded the low-lying plains. Then, as if a tap had been shut off, the rains would cease for months, leaving the land parched and thirsting under a relentless sun. In this environment of feast or famine, the Khmer engineers performed a feat of hydrological magic. They didn't just adapt to the water cycle, they tamed it, constructing an intricate network of canals, moats, and most spectacularly, gigantic reservoir lakes called barrays that turned the region around Angkor into a masterpiece of water management, allowing it to blossom into a pre-industrial megacity. The crown jewels of this system were the barrays themselves. These were not simple ponds, they were colossal, geometrically perfect artificial lakes, excavated by hand and surrounded by massive earthen dikes. The largest, the West Barray, is staggering to comprehend even today. Stretching over 5 miles long and 1.5 miles wide, it held over 50 million cubic meters of water, a volume that rivals a modern large-scale reservoir. Building this required moving an almost unimaginable amount of earth, all without machinery, a testament to the organizational power and sheer will of the Khmer civilization. But its purpose went far beyond mere storage. The barre was the beating heart of a vast, decentralized circulatory system, a complex network of canals, some large enough to be navigated by boat, connected these giant reservoirs to the countless smaller temple moats, community ponds, and rice fields that blanketed the Angkorian plain. This system functioned with a beautiful, multi-layered intelligence. During the intense monsoon season, the canals and barrays acted as a massive flood control mechanism. They captured the runaway surface water, preventing it from devastating the urban center and the intricate temple complexes. They slowed the water's flow, allowing silt and nutrient-rich sediment to settle out in the canals and reservoirs rather than being washed uselessly down the Siem Reap River. This captured silt was then periodically dredged and used to fertilize the fields, turning a problem into a resource. Then, as the dry season tightened its grip, the system reversed its role. The stored water in the barrays became a life-saving bank account. Gravity-fed canals and channels would gradually release this water, irrigating the vast rice paddies that fed the city's enormous population, which historians estimate may have been as high as 750,000 people at its peak. This ensured not just one, but multiple rice harvests per year, creating a surplus of food that supported a society capable of building Angkor Wat itself. The true sophistication, however, lay in the subtle engineering within the barrays. Recent archaeological studies using ground-penetrating radar and sediment cores have revealed that these reservoirs were not just simple, giant bathtubs. They were designed with a subtle slope and a series of internal channels and structures that managed water flow and quality. This design prevented stagnation, a critical concern in a tropical climate where standing water can quickly become a breeding ground for mosquitoes and disease. The scale and precision of this hydrological network reveal a profound understanding of the local topography. The Khmers engineered the entire Angkorian landscape on a gentle, consistent gradient, allowing them to move water by gravity alone across an area of over 1,000 square kilometers from the hills of the Kulin Plateau down to the Tonle Sap Lake. This was a system built to endure, to create a buffer against the unpredictable moods of the climate. It allowed Angkor to thrive for centuries, weathering periods of drought that would have crippled lesser cities. The lesson from the Khmer barrays is one of harmony and foresight. They didn't try to conquer their environment with rigid, forceful structures, but instead worked with its natural rhythms, creating a flexible, resilient system that provided food security, prevented disaster, and enabled the flowering of one of history's most magnificent urban civilizations. Now let's journey to a city that straddles two continents, a place where the very ground is a constant reminder of nature's power. Istanbul, formerly Constantinople, sits directly atop one of the world's most active seismic zones, a crossroads where multiple tectonic plates grind against one another. For centuries, this magnificent city has been shaken by devastating earthquakes that have toppled empires and flattened less resilient structures. Yet, against this backdrop of perpetual instability, the Ottoman Empire's master architects performed a miracle of balance and grace. They didn't just build mosques, they engineered ethereal, mountain-sized domes of stone that seemed to float weightlessly above the city, all while possessing a hidden flexibility that allowed them to dance with the tremors rather than fight them. The pinnacle of this achievement came from a genius named Mimar Sinan, the chief imperial architect for 3 sultans, who transformed the city's skyline with structures that were as scientifically profound as they were spiritually uplifting. Sinan's masterpiece, the Suleymaniye Mosque, is a perfect study in this seismic sleight of hand. At first glance, its enormous central dome, over 80 feet in diameter, appears to be a singular, impossibly heavy mass of stone and mortar. The intuitive fear is that during a quake, such a massive, concentrated weight would be the first thing to crack and come crashing down. But Sinan and his engineers understood that rigidity is the enemy in an earthquake. Their solution was one of brilliant distribution and calculated flexibility. The great central dome is not simply plopped on top of four walls. Instead, it is cradled by a cascading series of smaller half-domes, vaults, and massive but elegantly integrated buttresses. This created a graduated transition of weight and force, channeling the immense downward and outward thrust of the dome through a web of supporting elements that dissipated the energy safely down into the massive foundations. The geometry itself was a form of armor. The smooth, continuous curves of the domes and arches lack sharp corners or weak points where stress could concentrate and cause a catastrophic failure. When seismic waves roll through the ground, the entire structure is designed to sway as a unified, flexible entity. They used materials that could accommodate this movement, a special high-quality mortar with a degree of give, and carefully selected stones that could bear immense compression. The foundations themselves were engineered for the unstable ground, often reaching down to bedrock or using a grid of deep stone footings to prevent differential settlement during a shake. This was a holistic system where every element from the deepest foundation to the highest pinnacle worked in concert to absorb and redirect energy. The proof of this ingenuity is written in the very longevity of these buildings. The Suleimani Mosque has weathered countless major earthquakes since its completion in 1557, including the devastating 1766 quake that ruined large parts of the city. Each time it has settled may be cracked in non-critical areas, but its core structural integrity has never been compromised. It stands today, nearly 5 centuries later, not as a fragile relic but as a living, functioning place of worship, a testament to a design philosophy that saw earthquakes not as an obstacle to be overcome with brute force, but as a rhythmic force of nature to be harmonized with. Mimar Sinan's principles of weight distribution, flexible materials, and strategic geometry became the blueprint for Ottoman architecture, influencing the construction of hundreds of mosques across the empire. His work is now studied by modern structural engineers seeking inspiration for seismic-resistant design, proving that the most elegant solutions are often those that have already withstood the test of time and the tremors of the earth. Now let's travel to the heart of North America, to the vast floodplains of the Mississippi River, where a different kind of architectural genius was rising from the earth itself. Here, the great city of Cahokia, a bustling metropolitan center larger than London was at the time, faced an annual threat of inundation. The mighty Mississippi and its tributaries could overflow their banks with terrifying force, turning the fertile bottomlands into a swirling, destructive inland sea. The people of this region, often called the mound builders, responded not by constructing walls of stone, but by sculpting the very landscape into a form of protection. They built monuments not to reach the heavens, but to rise safely above the waters, creating an urban plan where resilience was literally baked into the ground beneath their feet. The most striking feature of Cahokia was its sprawling complex of earthen mounds, over 120 of them, dotting the landscape. The largest, known today as Monk's Mound, is a truly staggering feat of pre-industrial engineering. It covers over 14 acres at its base and rises in 4 terraces to a height of 100 feet, making it the largest man-made earthen mound north of Mexico. But its size isn't what made it ingenious, it was its function and construction. Monk's Mound wasn't just a hill, it was a massive, elevated platform, a carefully engineered foundation for the city's most important structures, likely the dwelling of the paramount chief and a temple that served as the spiritual heart of the community. By placing these critical buildings on this immense artificial plateau, the Cahokians guaranteed their safety from all but the most catastrophic floods. It was a brilliant form of vertical zoning, moving the essential organs of their society permanently out of harm's way. The construction process itself reveals a deep, practical understanding of soil mechanics and hydrology. These mounds weren't simply piles of dirt haphazardly dumped together. They were meticulously built in layers like a giant, stabilizing cake. Archaeologists have found evidence that the builders used different types of soil for specific purposes. They would often cap the mounds with a layer of heavy, impermeable clay. This clay acted as a natural waterproof barrier, like a roof for the entire structure. When heavy rains fell, this clay cap would shed water efficiently, preventing it from soaking deep into the mound's core where it could cause internal erosion, destabilization, or slumping. Beneath this protective layer, the mound was built up with baskets of soil and gravel, carefully compacted to create a solid, stable mass that would not easily wash away. This wasn't just about protecting a single building. The entire city's layout was a masterclass in water management. The Grand Plaza at the center of Cahokia, a vast open space covering nearly 50 acres, was actually intentionally sunken below the surrounding terrain. This might seem counterintuitive for a flood-prone area, but it was a deliberate and clever design. During heavy rains, this enormous plaza would act as a giant catchment basin, a temporary reservoir that would intentionally flood. By allowing the water to pool in this controlled, centralized location, the city planners effectively diverted it away from the residential areas and the bases of the all-important mounds. They channeled the water to where it could do the least damage, managing the deluge rather than trying to outright stop it. Furthermore, the mounds themselves, with their broad, flat tops, provided safe, dry gathering places for people during these flooding events, turning potential disasters into managed inconveniences. This incredible modification of the landscape represents one of the earliest and most sophisticated applications of what we now call geotechnical engineering. The Cahokians didn't have written manuals or advanced physics, but through generations of observation and experimentation, they developed an intuitive mastery of how different soils behave under saturated conditions. They understood drainage, compaction, and slope stability. They knew that a layered structure with a clay cap would hold its form, while a simple pile of topsoil would quickly be carved apart by runoff. Their mounds were more than just monuments. They were pragmatic, life-saving infrastructure. They transformed a vulnerable floodplain into a durable and resilient homeland, allowing a powerful and complex society to flourish for centuries by ensuring that when the rivers rose, their most sacred and vital spaces would remain high, dry, and secure. While the Cahokians were mastering the art of earthworks to stabilize their city on the Mississippi floodplains, an even more audacious architectural dream was taking shape on the other side of the world, a dream to build a magnificent city not on solid ground, but on top of water itself. Imagine the challenge faced by the first settlers of the Venetian lagoon. They sought refuge from invaders on a collection of marshy, low-lying islands separated by tidal channels. The ground was a soft, waterlogged mixture of clay and sand, a substance more like a thick soup than a foundation capable of supporting a simple hut, let alone the palazzos and cathedrals that would follow. Their solution was as counterintuitive as it was brilliant. Instead of trying to drain the water or avoid the unstable soil, they embraced it, driving millions of trees straight into the muck to create a hidden forest upon which an entire marble city would eventually float. The process began with an immense and coordinated effort. Teams of workers would first divert the water from a chosen site using temporary dams, a difficult task in itself with the constant tidal flow. Once exposed, the unstable surface layer of silt and mud was dug out until they reached the slightly more compact layer of clay beneath, known as caranto. This was the key. Into this firm clay base, they would drive long, pointed pilings, each one a tree trunk, stripped of its branches and bark. These weren't just any trees. They were predominantly alder, oak, or larch, chosen for their incredible resistance to rot and their straight, strong grain. Using heavy wooden mallets operated by teams in rhythmic unison, they would sink these logs one after another deep into the caranto, creating a dense forest of submerged timber. A single large building like the Santa Maria della Salute Church stands upon over 1 million of these individual pilings. The true magic, however, happened over time, hidden beneath the opaque water of the canals. When wood is submerged and deprived of oxygen, it doesn't rot in the conventional way. Instead, a remarkable process of petrification begins. The constant mineral-rich flow of salt water saturates the wood fibers, and over decades and centuries, the water slowly forces out the air and decay, causing microbes, replacing them with sediment and dissolved minerals. The wood doesn't turn to stone in the literal sense, but it becomes incredibly hardened, almost like rock, and completely immune to the biological processes that would normally cause it to disintegrate. This petrified forest of pilings became an incredibly stable and durable foundation, fused into the very clay of the lagoon bed. On top of this grid of pilings, the builders constructed a platform of horizontal wooden planks, and upon that they laid layers of stone, finally creating a stable, dry surface upon which to build their walls of brick and marble. This entire system was engineered for flexibility. The lagoon is a dynamic environment with constant tidal shifts, minor seismic tremors, and the gradual settling of sediments. A rigid foundation of stone alone would have cracked and collapsed under these shifting pressures, but the forest of wooden pilings had just enough give. They could flex and move minutely with the tides and the unstable substrate, allowing the heavy structures above to settle evenly without catastrophic fractures. It's a principle not unlike the Incas' flexible stonework, but applied to the very first layer of a building's contact with the earth. This hidden ingenuity is the sole reason Venice still stands today. For over 1,500 years, these petrified wooden foundations have defied the treacherous, waterlogged ground, supporting the immense weight of history and art, a silent testament to the power of understanding a material's hidden potential and designing not against nature's constraints, but ingeniously within them. Consider the sheer audacity of the Great Pyramid of Giza. For over 3,800 years, it stood as the tallest man-made structure on Earth, a monumental testament to a civilization that dared to build for eternity. In the harsh, wind-scoured desert of the Egyptian plateau, it faced a relentless onslaught of environmental threats, scouring sandstorms that could abrade solid rock, the occasional but potent tremors of the earth, and the brutal daily cycle of the sun, baking its surface by day and chilling it by night. That it still stands today, though stripped of its dazzling outer skin, is not a matter of luck. It is the direct result of some of the most meticulous, deliberate, and sophisticated engineering ever conceived, a masterclass in structural stability born from an almost supernatural understanding of geometry, materials, and the forces of nature. The first clue to its resilience lies in its breathtaking precision. The Great Pyramid is aligned to the 4 cardinal points with an error of just a fraction of a single degree. This near-perfect orientation is a staggering achievement of ancient surveying, but it was far more than a spiritual or astronomical statement. This precise alignment meant that the pyramid's immense weight, estimated at nearly 6 million tons, was distributed absolutely evenly across its vast square base. There were no inherent weak points created by a misaligned foundation. The force of gravity acted uniformly downward, creating a state of perfect equilibrium and preventing any one section of the base from bearing a disproportionate load that could lead to subsidence or a catastrophic shear failure, especially during a seismic event. This was combined with a brilliantly stable geometric form, the wide base-to-height ratio, the pyramid's low center of gravity and its shape, which channels compressive forces directly downward into the bedrock, make it incredibly resistant to toppling. It is the ultimate example of a structure designed to shed weight and force rather than resist it, but the true genius of the pyramid's design is hidden from view deep within its core. The internal network of chambers and passageways, often discussed for their mysterious purposes, also played a critical structural role. The Grand Gallery, with its complex corbelled walls, and the series of relieving chambers built directly above the king's chamber, function as a sophisticated system of pressure redistribution. The architects understood that the unimaginable weight of the masonry above couldn't simply rest on a flat ceiling. It would have crushed it instantly. So they designed these spaces to divert and channel the immense compressive forces around the open chambers, creating a series of arches and bridges within the solid stone that effectively relieved the pressure on the vulnerable voids below. It was an internal skeleton of strength, ensuring the pyramid's hollow spaces wouldn't become its points of failure. Perhaps the most ingenious feature, however, was the one that has been almost entirely lost to time: the brilliant white, polished Chura limestone casing stones that originally sheathed the entire structure. These were not merely for dazzling appearance. They were cut with such perfect, flat planes and fitted so seamlessly that the pyramid appeared as a single, smooth, gleaming mountain. This outer shell served a crucial engineering purpose. The tightly interlocking stones acted as a continuous structural skin, binding the entire edifice together and further distributing any external stresses. More importantly, their highly reflective, polished surface was a first line of defense against the desert sun. By reflecting a significant portion of the solar radiation, these stones prevented the extreme thermal expansion and contraction that daily heats and cools rock, a process that causes fatigue, microfractures, and eventual degradation in untreated stone. The casing kept the pyramid's core temperature more stable, protecting its structural integrity from the inside out. This combination of flawless alignment, internal pressure-relieving structures, and a protective, thermally regulating shell reveals a depth of holistic engineering thought that is humbling. The builders of the pyramids weren't just stacking stones. They were composing a symphony in stone where every element, from the grandest angle to the smallest joint, worked in concert to defy time itself. Now let's travel to the land of the rising sun, where ancient builders confronted a force of nature with a philosophy that seems almost counterintuitive. In a country shaken by thousands of earthquakes every single year, the instinct might be to build stronger, heavier, and more rigid structures to resist the shaking. But the master carpenters of ancient Japan understood something profoundly different. They realized that to survive the Earth's violent tremors, a building shouldn't fight back, it should dance. This revolutionary idea is embodied in one of Japan's most iconic and spiritually significant structures, the multi-storied pagoda. These elegant, seemingly fragile towers, built entirely of wood without a single nail, have withstood seismic assaults for over 14 centuries, not through brute strength, but through a breathtakingly elegant act of surrender. The secret to their resilience is a deceptively simple central pillar known as the Shinbashira. At first glance, this large, massive timber post appears to be the primary load-bearing column, holding up the entire pagoda. But that's the ingenious illusion. In many of these pagodas, the Shinbashira doesn't actually support the weight of the floors above it at all. Instead, it hangs suspended from the very top of the structure, dangling like a giant pendulum through a hollow core, its base resting on the ground but not firmly attached. When an earthquake strikes and the ground begins to lurch violently, the pagoda's box-like floors, built with incredibly flexible interlocking joints, are designed to sway independently. This is where the magic happens. The heavy, suspended Shinbashira begins to swing in the opposite direction of the building's sway. This creates a powerful counteracting force, a rhythmic push and pull that dampens the earthquake's energy and prevents the pagoda from ever swinging too far in one direction. It's a perfect passive damping system, a built-in seismic shock absorber that requires no power, no sensors, and no human intervention. This brilliant system is made possible by the other cornerstone of traditional Japanese woodworking, the art of the joinery. These pagodas are complex three-dimensional puzzles, assembled using hundreds of different types of interlocking wooden joints. There are no nails, no metal brackets, no glue. The entire structure is held together by friction, precision, and the perfect fit of carved wood. During an earthquake, these joints don't remain static. They flex and groan, absorbing and dissipating vibrational energy throughout the entire framework. The wood itself, often resilient cypress or cedar, has a natural elasticity that allows it to bend without breaking. This combination creates a building that moves as a unified yet flexible whole, swaying with the seismic waves like a tree in a storm, allowing the energy to pass through it harmlessly rather than concentrating into destructive force at any single weak point. The 5-story pagoda at Horyuji Temple, built in the 7th century, is the oldest surviving wooden building in the world, and it stands as the ultimate testament to this technology. It has weathered an estimated 1,500 years of tremors, including some of the most powerful earthquakes in Japanese history, and it remains standing, tall and serene. Modern engineers, armed with sensors and computer models, have studied these ancient structures and confirmed their effectiveness, leading to a paradigm shift in how we design for earthquakes today. The principle of base isolation, where modern buildings are placed on flexible bearings or sliders to allow them to move independently of the shaking ground, is a direct descendant of the pagoda's flexible joints. The tuned mass damper, the giant counterweight pendulum you'll find swaying at the top of skyscrapers like the Taipei 101 to stabilize it against wind and quakes, is the high-tech grandchild of the humble Shinbashira. These ancient builders, through keen observation and a deep respect for the materials they used, unlocked a secret of physics that we are only now fully appreciating with all our advanced science. They taught us that true strength isn't always about rigidity and resistance. Sometimes the most powerful way to overcome a force is to yield to it gracefully, to move with it, and in doing so, to rob it of all its destructive power. But the mastery of the Mesopotamian engineers extended far beyond simply building walls of earth to hold back the river. Their true genius lay in their holistic and integrated approach, viewing the entire river system as something to be managed and coaxed into productivity, not just fought against. The levees themselves were just the first line of defense in a sprawling, carefully orchestrated network of hydraulic engineering. From these primary embankments, they carved a vast, branching web of secondary and tertiary canals, meticulously planned to act as both a pressure release valve for floodwaters and a life-giving artery for their fields. When the snowmelt from the distant Anatolian mountains sent a surge of water down the Euphrates, the levees would contain the initial onslaught, but the controlled flow of water into these canals prevented the banks from being overtopped or breached. This water was then directed into the fields, performing the dual miracle of irrigation and fertilization. The Tigris and Euphrates are silt-laden rivers, and as this diverted water spread across the farmland, it would slowly deposit a fresh layer of incredibly rich, mineral-heavy silt, naturally renewing the soil's fertility year after year. This process of controlled siltation was the secret engine of Mesopotamian agriculture, turning what could have been a destructive force into the very foundation of their surplus and their civilization's growth. This incredible system did not build or maintain itself. It required a level of social organization and collective effort that was unprecedented in the ancient world. The construction and, more importantly, the ongoing maintenance of these earthworks became the responsibility of the entire community, organized under the direction of temple priests and later royal administrators. Canals would silt up, levees would erode, and channels would need constant clearing. This created a powerful social contract. Every farmer who benefited from the water and the protection was expected to contribute labor to its upkeep. This collective endeavor, this shared investment in a common good, was arguably as revolutionary as the engineering itself. It forged a sense of shared identity and purpose, moving society from isolated village life toward the complex, coordinated effort required for urban civilization. The need to manage this water infrastructure is one of the key theories for the rise of some of the world's first centralized governments and systems of writing, as accounting for labor and distributing water rights required meticulous record-keeping. The legacy of these early hydraulic engineers is not confined to the dust of history. It is etched into the landscape of modern agriculture and urban planning. The fundamental principle of using earthen embankments to control river flow is still the cornerstone of flood management along mighty rivers like the Mississippi, the Nile, and the Yangtze. While our materials may have evolved to include concrete and steel, the core idea remains unchanged. Guide the water, don't just block it. Furthermore, the Mesopotamian understanding of irrigation canals directly informs the vast networks that water the breadbaskets of the world today, from the Central Valley of California to the fields of Punjab. Their most profound lesson, however, might be one we are still struggling to fully relearn. Their system worked in harmony with the river's natural cycles, using its energy and its gifts to their advantage. In contrast, some modern dam-centric approaches have often tried to completely dominate and alter river systems, leading to unintended consequences like the loss of silt deposition downstream, which causes delta erosion and the loss of fertile land. The Mesopotamians show us that the most resilient engineering isn't about winning a war against nature, but about cleverly negotiating a lasting peace, one that channels nature's immense power into a force for sustained life and growth. Imagine standing on a steep Andean mountainside where the slope is so sheer that it seems nothing could possibly grow here. The thin air bites with cold and the threat of landslides feels ever present. This was the raw, intimidating canvas upon which the Inca civilization decided to paint its agricultural masterpiece. They looked at these vertiginous slopes not as uninhabitable wastelands, but as untapped potential. Their solution was a breathtaking transformation of the very mountains themselves, the construction of vast steppe terraces that ribboned across the Andes, turning treacherous inclines into some of the most productive and resilient farmland the ancient world ever knew. This was far more than simple farming. It was a profound act of ecological engineering, a declaration that human ingenuity could forge abundance from the most challenging of environments. The primary genius of these terraces, known as Andeans, was their revolutionary approach to erosion control. In the rugged Andes, heavy tropical rains were a constant threat, capable of washing the precious, thin topsoil straight down the mountain in a matter of minutes, leaving behind barren rock. The Incas halted this destructive process with elegant, stone-walled steps. They built robust retaining walls from precisely cut stones, fitting them together without mortar in the same seismic-resistant technique used in their buildings. These walls did more than just create flat planting surfaces. They acted as a series of massive, interconnected barriers. When the rains came, the walls stopped the downhill flow of water and soil dead in its tracks. The water was forced to percolate slowly downward through the loose, rocky fill behind each wall, rather than sheeting off the surface in a destructive torrent. This process effectively trapped the soil and nutrient-rich sediment exactly where it was needed, within each level of the terrace, while the slow filtration replenished the groundwater instead of causing flash floods in the valleys below. They didn't just farm the land, they engineered it to hold itself together against the elements. But the magic of the Andes extended far beyond simply holding the mountain in place. The Incas were masters of microclimate creation. The varying elevations, sun exposures, and wind patterns across a single terraced mountainside allowed them to cultivate a stunning diversity of crops that would never normally grow side by side. A lower, warmer terrace might be perfect for growing maize, while a slightly higher, cooler level could support quinoa or potatoes. At the highest elevations, they could pasture llamas and alpacas. This agricultural biodiversity was their ultimate insurance policy against famine. If a late frost wiped out the potato crop on one level, the maize on a lower, warmer terrace might still thrive. If a disease affected one variety of plant, dozens of others remained untouched. This system created a highly resilient and redundant food web, insulating their society from the catastrophic crop failures that could doom other civilizations. The true sophistication, however, lay in their integrated water management. These terraces were not isolated agricultural plots. They were components of a grand, mountain-wide hydraulic system. The Incas constructed intricate canals and aqueducts to channel meltwater from high-altitude glaciers down to their fields. This water was then distributed with incredible precision from one terrace level to the next through a series of carefully managed stone conduits. They could control the flow to individual plots, ensuring every plant received the moisture it needed without any waterlogging or waste. This gravity-fed irrigation was a masterpiece of passive engineering, turning the entire mountainside into a self-regulating, sustainable agricultural machine that required no pumps or external power, only the intelligent application of natural forces. This approach stands in stark contrast to modern large-scale agriculture, which often tries to flatten and homogenize the landscape, forcing it to conform to the needs of machinery and monoculture. The Incas did the opposite. They adapted their methods to the land's natural form, working with the slopes rather than against them. They understood that the mountain's greatest vulnerability, its steep, erosion-prone gradients, could be transformed into its greatest strength through thoughtful design. Each terrace wall absorbed the sun's heat during the day and radiated it back at night, protecting delicate plants from frost. The system as a whole created a stable, productive, and beautiful landscape that has endured for centuries, long after the empire itself faded. The Andes are more than ancient ruins. They are a living lesson in sustainable land use, demonstrating that the most powerful way to defy natural disasters is not through brute force opposition, but through a graceful and intelligent collaboration with the environment. Now let's step into the shadow of a colossal stone arch, a shape so familiar it feels almost elemental, yet its true power was unlocked by the Romans in a way that would forever change the face of the earth. Before their innovations, ancient builders were largely confined to the limitations of the post and lintel system. Think of Stonehenge, with heavy horizontal beams resting on vertical supports, creating structures that were strong but created narrow, cramped spaces, vulnerable to collapse if the lintel cracked or the supports shifted. The Romans looked at this problem and saw a more elegant solution in a form they didn't invent, but which they perfected with relentless, practical genius: the arch. They understood that an arch wasn't just a beautiful curve. It was a masterpiece of physics, a mechanism for transforming crushing downward weight into outward thrust, and then mastering that thrust to create spaces of breathtaking scale and durability. The secret of the arch lies in its central wedge-shaped stone, the keystone. When the keystone is slotted into place at the apex, the weight of the entire structure above it is transferred down through the voussoirs, the other arched stones pushing them tightly together under immense compression. This force is then channeled diagonally outward and down into the massive piers or abutments on either side. The arch literally pushes against itself, creating a state of perfect, self-supporting tension. The Romans realized that by repeating this powerful form side by side, they could create a barrel vault, a long, continuous arched ceiling. And by intersecting two barrel vaults at a right angle, they created the groin vault, which concentrated the weight onto the four corners of the space below, freeing up the walls from bearing load and allowing for the creation of vast, open interiors and the installation of large windows. This was the revolutionary leap, moving from buildings defined by their walls to spaces defined by their soaring, weightless ceilings. They then combined this brilliant geometry with their other miracle material, Roman concrete. While the arch and vault handled the compression, the concrete acted as a monolithic plastic binder. When poured into wooden frameworks to form vaults and domes, it hardened into a single, continuous, incredibly strong shell without the weak points of mortar joints. This marriage of form and material is what allowed them to build on an unimaginable scale. The Colosseum, with its 3 tiers of superimposed arches, wasn't just an amphitheater, it was a lesson in load distribution. Each arch channeled the weight of thousands of spectators and the massive stone seating down through the piers, creating an incredibly stable and open structure that could withstand tremors. If one section was damaged, perhaps by fire or a minor quake, the failure was localized and wouldn't trigger a catastrophic chain reaction collapse of the entire building. The same principles allowed aqueducts like the Pont du Gard to stride across valleys, their multi-tiered arches gracefully carrying the weight of the water channel above while resisting the flow of floodwaters below. The arches in the lower level are wider and more robust to handle the greater load, while the upper tiers become progressively narrower and lighter, a perfect demonstration of calculated structural efficiency. This architectural DNA, encoded in stone and concrete, became the blueprint for resilience. It allowed Roman bridges to stand for millennia because their arch design let floodwaters pass through with minimal resistance, unlike solid causeways that would be swept away. It enabled the vast, column-free interior of the Basilica of Maxentius, a space that would have been inconceivable just centuries before. The Roman mastery of the arch and vault was more than a construction technique. It was a new way of thinking about space, strength, and permanence. They taught the world how to build not just for the present, but for the ages, creating a legacy of resilient design that echoes in every arched bridge, every vaulted train station, and every domed Capitol building that followed, proving that true strength is found not in resisting force, but in redirecting it with intelligent, graceful form. While Roman arches soared upward to distribute weight and Inca terraces climbed mountainsides to prevent erosion, the engineers of ancient India were digging down, creating breathtaking subterranean cathedrals dedicated to a single, life-giving resource: water. In the arid and semi-arid regions of western India, particularly in Gujarat and Rajasthan, the rhythm of life was dictated by the brutal pendulum swing of the monsoon. For a few months, the skies would open, delivering torrential rains that would quickly run off the hard-baked earth, often causing flash floods. Then, for the rest of the year, the land would parch under a relentless sun, with surface water vanishing and groundwater retreating deep into the earth. Survival here required a different kind of ingenuity, one that didn't fight the drought but instead dove deep to meet it. Their solution was the stepwell, known as a vav or bayoli, and one of the most magnificent examples is the 11th century Rani Kai vav, or the Queen's stepwell in Patton. Unlike a simple well, which is merely a vertical shaft, a stepwell is a complex, multi-story underground structure, an inverted temple where the divinity is water itself. The design is a masterpiece of hydrological logic and social architecture. As you approach Rani Kai vav from ground level, it appears as a long, rectangular trench sunk into the earth. But then you begin the descent, moving down a grand central staircase that broadens as it goes deeper. On either side, symmetrical steps fan out, creating a stunning geometric pattern that draws the eye downward. This is not just for aesthetic drama. Every single step serves a critical purpose. During the peak of the dry season, as the water table plummeted sometimes over 100 feet below the surface, the receding water would become increasingly difficult to reach. The step design meant that no matter how far the water level dropped, there was always a staircase leading right down to it, ensuring access for people to collect water even during the most severe droughts. It was a system built for resilience in the face of nature's most extreme fluctuations. The construction of these stepwells was a feat of geotechnical engineering. Digging such a massive, deep, open excavation without modern machinery was perilous work, with constant risk of collapse. The builders countered this by lining the entire structure with precisely cut stone blocks, creating strong, retaining walls that held back the earth. But they went far beyond mere functionality. The walls of Rani Kai vav are a sprawling gallery of exquisite sculpture, featuring hundreds of intricate carvings of deities, celestial nymphs, and mythological scenes. This artistic splendor was not merely decorative, it served a vital structural and protective role. The dense, interlocking carvings and the deeply incised patterns actually helped to reinforce the stonework, much like the ribs of a Gothic cathedral, distributing stress and adding strength to the walls that were holding back immense lateral earth pressure. Furthermore, the entire structure was designed as a cool, subterranean sanctuary. By going deep underground, the water was shielded from the scorching sun above, dramatically reducing evaporation loss, a constant threat in such a hot, dry climate. The stone mass of the surrounding walls also acted as a natural cooler, keeping the water at a refreshingly low temperature even during the hottest months. The true sophistication of the stepwell, however, extended into the realm of water management and purification. Many stepwells were not just passive reservoirs, they were actively integrated into the local hydrology. They were often strategically positioned to collect surface runoff from a large catchment area during the brief monsoon rains, channeling this precious water into the deep storage tank. Some featured sophisticated filtration systems at the inlets, using layers of sand and gravel to sieve out silt and debris before the water entered the main well, helping to keep the water cleaner for longer. The sheer volume of these structures acted as a massive groundwater recharge point, allowing collected rainwater to percolate slowly back into the aquifer, replenishing the very source it drew from. This created a sustainable cycle of capture, storage, and recharge. In a world where a failed monsoon could mean famine and societal collapse, these stepwells were far more than just architectural wonders. They were the beating heart of the community, ensuring a reliable year-round water supply for drinking, bathing, and irrigation. They were places of social gathering, religious ceremony, and respite from the heat, a stunning testament to a civilization that understood that to truly master water, you must first honor it, and in doing so, build a legacy of resilience that would quench the thirst of generations. While the stepwells of India reached deep into the earth to secure a lifeline against drought, another ancient culture looked out across the shimmering surface of their lakes and saw not a barrier but a promise of safety. In the wetlands and lochs of Scotland and Ireland, the Celts faced a double-edged sword. The very fertility of the river valleys that supported their agriculture also made them devastatingly vulnerable to seasonal flooding, while the rich farmland was a constant lure for rival clans and raiders. Their ingenious solution was to turn their greatest vulnerability, the water itself, into their strongest defense. They became masters of a unique form of amphibious architecture, building entire fortified homesteads on their own personal islands, known as crannogs, in a stunning display of strategic location and environmental adaptation. Constructing a crannog was a monumental community effort, a testament to both collective will and engineering savvy. The process began on the shores of a lake or in a sheltered, slow-moving river estuary. Teams would first gather enormous quantities of stone boulders, rocks, and rubble, and load them onto wooden barges or rafts. They would pole these vessels out to a carefully chosen spot, often a natural shoal or a shallow underwater rise, and then begin the painstaking work of dumping this stone into the water to create a wide, stable, circular foundation on the lakebed. This wasn't a haphazard pile. It was a deliberately built mound designed to rise above the waterline. On top of this stone base, they would drive sharpened wooden piles deep into the soft sediments, lashing them together to create a sturdy wooden palisade that contained the stone core and formed a defensive wall. The interior of this ring was then filled with layers of brushwood, peat, clay, and more stones, all meticulously packed down to create a solid, dry, and surprisingly stable artificial island. The entire structure was essentially a giant, buoyant raft of organic and stone material, anchored in place by its own immense weight and the surrounding piles. The single-family roundhouse that crowned this island was a marvel of insulation and strength, typically built with a stone foundation and walls of wattle and daub or sturdy timber, topped with a conical thatched roof. But the true genius of the crannog was not just the house itself, but its relationship to the surrounding water. By placing their home hundreds of feet from the shore, the inhabitants achieved a powerful form of disaster avoidance. Seasonal floods that would sweep through the river valleys, destroying crops and washing away riverside settlements, would simply cause the water level around the crannog to rise slightly, leaving the dwelling itself high, dry, and completely secure. The crannog turned the destructive force of flooding into a harmless inconvenience, a mere change in the view from the front door. This aquatic location offered a second, equally critical layer of security, defense. In a landscape of frequent tribal conflict, the crannog was a natural fortress. The surrounding water acted as a wide, daunting moat, forcing any potential attacker to abandon a stealthy approach and navigate a slow, vulnerable crossing by boat or by wading, all while under the watchful eyes of the defenders. The only access was typically a single, narrow stone causeway that zigzagged just below the water's surface, known only to the residents. This hidden pathway could be easily blocked or defended by just a few people, making a direct assault extremely costly. The crannog dwellers could literally pull up the drawbridge by simply removing a few planks from their hidden causeway, isolating themselves in a secure, self-contained stronghold until any threat had passed. This dual-purpose design, elevation against floods and isolation against enemies, showcases a holistic approach to risk management, where one single architectural solution provided a powerful answer to two completely different kinds of threats. Life on a crannog was a testament to a deep, symbiotic relationship with the wetland environment. The lake provided not just protection but sustenance. The inhabitants were expert fishermen and hunters of waterfowl, and the fertile waters yielded reeds and rushes for thatching and basketry. The very act of building the crannog also enriched the surrounding ecosystem. The nutrient-rich refuse from daily life, discarded over the wooden walls, created ideal habitats for fish and other aquatic life, essentially farming the lake around them. While it required more daily effort to ferry supplies and people to and from the shore, the trade-off was deemed worth it for the unparalleled security and the rich resources the lacustrine environment provided. These artificial islands were more than just quirky homes. They were a sophisticated and highly successful adaptation, a clever manipulation of a landscape that allowed Celtic families to not just survive, but to thrive securely for generations, surrounded by the very element that threatened to displace them. From the cool, submerged forests supporting Venice to the breezy heights of Japanese pagodas, ancient engineers consistently found ways to turn environmental challenges into advantages. Now journey to the sun-scorched coasts of the Persian Gulf, where the very air can feel like a furnace and the shimmering heat haze distorts the horizon. Here, in one of the most thermally punishing climates on Earth, architects faced a paradox: how to create livable, comfortable spaces without access to the two things modern cooling relies on: abundant electricity and even more scarce fresh water. Their breathtakingly elegant solution was to build houses that could breathe, using a clever architectural feature known as the wind tower, or bagia, that transformed still, suffocating air into a refreshing, natural air conditioning system. The principle behind the wind tower is a masterclass in passive thermodynamics, harnessing the natural movement of air without a single moving part or watt of energy. A bagia is essentially a tall, chimney-like structure rising high above the roof of a building, but with a critical design feature. It is open on multiple sides, typically 4, though sometimes 2 or 8, depending on the prevailing wind patterns. These openings are positioned to capture even the faintest breeze from any direction high above the ground, where the air is less obstructed and often moves more freely. As this slightly cooler, faster-moving air is caught by the tower, it is funneled downward through the shaft. The genius of the system is its partnership with the building's interior layout and another ancient cooling method, the Kanat or water reservoir. Often, the base of the wind tower shaft would open directly over a small indoor pool of water or a channeled stream. As the captured wind is forced down the tower and across the surface of this water, it undergoes an evaporative cooling effect. The air picks up moisture molecules, a process that requires energy and thus draws heat from the air itself, significantly dropping its temperature before it spills out into the living quarters below. But the system doesn't stop there. It operates in a beautiful, continuous cycle. The now cooled, denser air flows into the rooms, displacing the hotter, lighter air inside. This warm air naturally rises, seeking an escape route. Designers provided this exit through strategically placed vents or a second, single opening tower positioned on the opposite side of the building. This second tower acts as an exhaust, creating a constant suction that pulls the hot air up and out. The entire home becomes a self-regulating ecosystem of air circulation, with the wind towers acting as lungs, one inhaling cool air, the other exhaling warm air. This creates a gentle, continuous breeze throughout the structure, maintaining a comfortable temperature even when the outside air is blisteringly hot. The materials used were also part of the design. Thick, mud brick walls with high thermal mass would absorb the coolness of the night air and slowly release it throughout the day, working in concert with the towers to stabilize the indoor climate. The impact of this invention on public health and societal sustainability cannot be overstated. In a region where water was more precious than gold, the badger offered a cooling solution that required only a minimal amount for evaporation, a stark contrast to the water-intensive swamp coolers of today. It prevented heat stroke and made dense urban living possible in an otherwise lethal environment. Cities like Yazd in Iran, often called the City of Windcatchers, are living museums of this technology, with their skylines punctuated by these elegant towers. What's truly remarkable is that this ancient approach to climate control is experiencing a powerful renaissance in contemporary sustainable architecture. Modern architects and engineers grappling with the enormous energy demands of mechanical air conditioning are looking back to the badger for inspiration. The principles of passive cooling, cross-ventilation, and evaporative cooling are being integrated into the design of new buildings, from private homes to large commercial complexes, drastically reducing their carbon footprint and operational costs. The wind tower stands as a timeless reminder that sometimes the most advanced and sustainable technology isn't about creating new energy, but about intelligently harnessing the natural forces that are already and always there for us to use. Imagine walking through the labyrinthine corridors of the Palace of Knossos on the island of Crete, a complex so vast and intricate it gave birth to the myth of the Minotaur's maze. The walls are covered in vibrant frescoes of leaping dolphins and graceful athletes, but the true marvel isn't just the art, it's the very air you breathe. Despite being a sprawling, multi-story stone structure housing hundreds of people, the atmosphere feels surprisingly fresh and light, not damp and stagnant. This was no accident. The Minoan civilization, which flourished over 3,500 years ago, were pioneers of healthy living architecture, and their most ingenious trick was designing their palaces not as sealed fortresses, but as buildings that could breathe. They achieved this through a sophisticated system of light wells and open courtyards, creating a passive environmental control system that promoted well-being and preserved their structures for centuries. At the heart of this design was the central courtyard, the absolute core around which the entire palace was organized. This large, open-air space functioned as the lungs of the building. But the Minoans didn't stop there. They perforated the palace with numerous smaller lightwells, vertical shafts that ran from the roof down through multiple stories. These weren't just simple holes for light. They were carefully engineered components of a natural ventilation system. The principle at work is one we now call stack ventilation, or the chimney effect. As the sun heated the air in the central courtyard, that air would become warmer and rise. This rising column of warm air created a suction effect, pulling cooler, fresher air from the lower levels of the palace into the courtyard. To facilitate this flow, the Minoans strategically positioned corridors, doorways, and porticos to act as airways, ensuring there was a clear path for air to move from the periphery of the building toward its central core, and then upward and out. This constant, gentle exchange of air prevented the buildup of stale odors, humidity, and the dangerous mold spores that can cause respiratory illnesses and degrade organic materials like food, textiles, and even the wooden structural elements within the walls. The battle against humidity was particularly critical for the Minoans. Their island home in the Mediterranean was blessed with a pleasant climate, but it was also surrounded by sea air, which carries salt and moisture, two silent assassins for any building. Dampness seeping into stone and brickwork can lead to efflorescence, where salt crystals form and expand within the pores of the stone, eventually causing it to crumble and spoil. More insidiously, persistent humidity creates the perfect breeding ground for destructive molds and fungi that can rot wooden beams and weaken structures from the inside out. The Minoan lightwell system was a brilliant defense against this by ensuring a continuous flow of air through the deepest parts of the palace. They kept the relative humidity low. Walls were able to dry out after periods of rain, and moisture never had a chance to stagnate. This significantly reduced the rate of environmental decay, contributing to the remarkable fact that substantial portions of these complex structures are still standing today, millennia after they were built. Furthermore, this architectural strategy provided exceptional thermal comfort long before the concepts of insulation or air conditioning existed. The massive stone walls of the palace had high thermal mass, meaning they absorbed heat slowly during the day and released it slowly at night. The lightwells and courtyards complemented this perfectly. In the hot summer months, the shaded lower levels, constantly fed by cooler air drawn from these sunken spaces, remained refreshingly temperate. The design also facilitated passive cooling. The movement of air across the skin has a pronounced cooling effect, and the Minoans enjoyed this benefit constantly. In the winter, they could likely adjust the airflow by using movable screens or hangings over certain openings to control drafts while still allowing light to penetrate. This holistic approach to climate control created a living environment that was not only healthy but also genuinely comfortable year-round, enhancing the quality of life for its inhabitants and showcasing a sophisticated understanding of human bioregulation. The legacy of Minoan architectural wisdom is profoundly relevant today. In an age where we seal ourselves in glass and steel boxes reliant on massive energy-consuming HVAC systems to maintain air quality, the Minoan model offers a powerful lesson in sustainable, passive design. Modern architects pursuing green building certifications like LEED are now revisiting these ancient principles, incorporating atriums, solar chimneys, and strategically placed ventilation shafts to reduce a building's mechanical cooling load and improve indoor air quality naturally. The Palace of Knossos stands as a timeless testament to the idea that the health of a building and the health of its occupants are inextricably linked, and that sometimes the most advanced environmental solution is to simply let the fresh air and light do the work they have always done. Now imagine a different kind of sanctuary, one not built from the ground up, but revealed by carving away everything that it is not. In the highlands of northern Ethiopia, in a place called Lalibela, you will find a cluster of 11 churches that defy all conventional logic of construction. They are not assembled from quarried stone, they are the stone. In the 12th century, under the direction of King Jeba Meskel Lalibela, master craftsmen undertook a project of almost unimaginable ambition and patience. They didn't build up, they carved down directly into the living volcanic rock of the mountainside, sculpting these sacred spaces from the top of the rock formation downward, in a monumental act of subtraction that created some of the most structurally resilient buildings ever conceived. The process itself was a breathtaking feat of reverse engineering and faith. Workers would first trench deep moats around a single, massive block of solid basalt, completely freeing it from the surrounding bedrock. Then, like master sculptors revealing a form trapped within marble, they would begin the painstaking work of hollowing out the interior of this giant block. They carved out the naves, the columns, the altars, and the domes, all from the inside, working for decades in the dim light, removing an estimated 100,000 cubic tons of rock. The result is not a building in any traditional sense, but a monolithic structure, a single, continuous piece of stone that is both the form and the substance of the church. This is the ultimate expression of architectural resilience. You cannot knock down a wall that is still part of the mountain. You cannot collapse a roof that is the skyward side of the same unbroken stone. This makes the churches of Lalibela virtually immune to the very disasters that have toppled countless cathedrals and temples. Earthquakes that would shake a constructed building to its foundations merely cause these monolithic forms to tremble as one with the earth they are still a part of. Fire has nothing to burn, as there is no timber, no thatch, no flammable material whatsoever in the primary structure. The very concept of erosion is turned on its head. While wind and rain weather the surface, they cannot erode the structural integrity of a form that has no joints, no mortar, and no separate components to weaken and fail. Yet, even carved from a single mighty piece of rock, these churches were not left completely to the elements. The builders demonstrated a sophisticated understanding of hydroengineering, proving that even a solid stone building has a vulnerability: water. The volcanic rock is porous, and without protection, water seeping into tiny cracks could freeze and expand over centuries, or simply sit and stagnate, leading to degradation. The solution was a network of meticulously carved drainage channels and aqueducts. These weren't added on, they were integrally carved into the same rock, designed to catch rainwater and channel it away from the sacred spaces, directing it swiftly off the roofs and down into the deep trenches that surround each church. These trenches themselves act as massive moats, preventing surface water from pooling around the foundations and ensuring the ground remains stable and dry. This holistic approach to water management protected the churches from their only true environmental threat, ensuring their interior spaces remained pristine and dry for centuries. The endurance of these structures is a powerful testament to a philosophy of working with nature rather than against it or simply upon it. The builders of Lalibela didn't see the mountain as a quarry from which to extract materials. They saw it as the finished product already in potential form, waiting only for the excess to be removed to reveal the glory within. This approach created a permanence that is almost unique in the architectural world. They didn't impose an external design onto a landscape. They revealed a design that was already inherent in it, resulting in a harmony between structure and site that is both profound and practically unshakable. In an age where we often think of resilience as adding more reinforcement, more steel, more complex systems, the churches of Lalibela offer a humbling and elegant counterpoint. They teach us that the most resilient structure might not be the one that is most complexly built, but the one that is most simply and completely unified with the very earth it stands upon, a timeless sanctuary born not from addition but from revelation. Now let's journey to the misty mountains of Sichuan province in ancient China, where over 2,200 years ago, a governor named Lai Bing faced what seemed like an impossible and heartbreaking cycle of suffering. The Min River, flowing down from the Himalayas, was a temperamental giant. Each summer, torrential rains and snowmelt would swell its banks, unleashing catastrophic floods that drowned the fertile Chengdu plains, wiping out entire villages and seasons of crops. Then, as if to mock the survivors, the river would retreat, leaving behind a parched landscape desperate for water, unable to irrigate the fields that would prevent famine. This brutal pendulum swing between deluge and drought was choking the potential of the entire region. Lai Bing's mandate from the Qin emperor was not to wage war on the river, but to broker a lasting peace. His solution, the Duzhongyan irrigation system, stands today not as a rusting relic, but as a living, breathing testament to a philosophy of engineering that works in concert with nature, not against it, and it remains fully operational, watering farms to this very day. The sheer brilliance of Duzhongyan lies in what it doesn't have: a massive dam. Instead of attempting to block the river's formidable power with a single, vulnerable point of failure, Li Bing and his son devised a system of elegant, decentralized components that gently coaxed the water into behaving. The first and most dramatic element was the yuzui, or fish mouth levee. This was a long, man-made divider constructed from enormous bamboo cages filled with stones, which was strategically placed in the center of the river. This seemingly simple structure performed a miraculous act of hydrological judo. Its curved tip, resembling the nose of a fish, would split the powerful current into two streams, an inner stream and an outer stream. During the dry season, a larger portion of the water was naturally diverted into the narrower, deeper inner stream, which was the one designated for irrigation. But during the flood season, the river's volume would increase so much that the majority of the raging water was forced into the wider, shallower outer stream, which acted as a spillway, safely carrying the excess volume away. This was a self-regulat Chinese letter Fenliu or Chinese letter system, a perfect example of using the water's own energy and volume to manage itself, but controlling the water's path was only half the battle. The Min River carries a colossal amount of silt and sediment down from the mountains, which could quickly clog any irrigation channel and render it useless. This is where the second marvel, the Phasian or flying sand spillway, comes into play. This was a low weir, a carefully calibrated notch built into the inner riverbank. Its height was the product of meticulous calculation. During normal flow, the water would simply flow over it and continue down the main irrigation channel. However, during a flood, when the water level in the inner stream rose dramatically, the Phasian would spring into action. The sudden, increased pressure and velocity would cause the water to jet over the spillway with tremendous force, but it also created a powerful whirlpool effect. This whirlpool acted like a natural centrifuge, sucking up the heavier silt and sand that had settled to the bottom and violently ejecting them over the spillway and back into the main river's outer stream. This automatic desilting mechanism ensured that the irrigation channels remained clear and flowing without any need for human dredging. It was a perpetual motion machine for sediment removal, powered entirely by the river itself. The final piece of this hydraulic puzzle was the Bayapingku, or precious bottleneck channel. This was the crucial gateway, a narrow passage cut directly through a towering mountain of solid rock. This channel was the only entrance to the vast irrigation network that would water the Chengdu Plains. Its narrow, constricted design served a vital purpose. It acted as a final check, a natural throttle that precisely controlled the amount of water entering the system. It prevented the entire network from being overwhelmed during high water, ensuring a smooth, manageable flow to the farms below. The story of how workers 2 millennia ago managed to cut through this mountain without modern explosives is a legend in itself. They are said to have used a method of heating the rock with fire and then rapidly cooling it with water, causing it to crack and fracture, allowing them to slowly, painstakingly chip it away over an 8-year period. This incredible perseverance underscores the long-term vision behind the entire project. This was not a quick fix, but a permanent foundation for prosperity. The legacy of Duzhongyan is almost immeasurable. It transformed Sichuan from a land plagued by disaster into one of China's most productive and stable agricultural heartlands, earning it the name Land of Abundance. It protected the plains from floods and irrigated the fields that fed a growing empire, directly contributing to the power and expansion of the Qin dynasty. But its most profound lesson is its sustainability. Unlike modern mega dams that often alter ecosystems, displace communities, and trap silt, leading to downstream erosion and other problems, Duzhongyan is a model of ecological engineering. It respects the river's natural flow, works with its energy, and has maintained a perfect dynamic balance for over 2 millennia. It requires maintenance, of course, but its core design has never needed a fundamental overhaul. It stands in quiet, powerful contrast to the often forceful, interventionist approach of modern civil engineering, reminding us that the most elegant and enduring solutions are those that listen to nature, learn its rhythms, and gently guide its power for the benefit of all. Now imagine yourself as a Norse sailor, enveloped in the oppressive gray of a North Atlantic squall. The sky and sea merge into a single, featureless void. The wind howls, and your wooden longship is tossed on waves as tall as hills. Every known landmark has vanished. In this disorienting gloom, with no sun or stars to guide you, the threat of sailing endlessly in circles or onto a rocky shore becomes terrifyingly real. This was the daily reality for Viking explorers, and their ingenious solution to this existential problem was not a complex instrument, but a seemingly mundane crystal pulled from the earth. They called it a solarstein, a sunstone, and its ability to reveal the hidden sun through the thickest overcast was nothing short of navigational magic, a brilliant application of optical physics that turned a catastrophic blind voyage into a calculated, manageable journey. The genius of the sunstone lies in a fascinating property of certain crystals like calcite or Icelandic spar, known as birefringence or double refraction. When a beam of light enters a calcite crystal, it doesn't simply pass through. It splits into two separate rays of light, each vibrating in a different plane and taking a slightly different path. To the naked eye, if you were to place a calcite crystal over a single dot, you would see two dots. The Vikings discovered that by rotating such a crystal while pointing it toward the sky, even on a completely overcast day, they could detect the hidden polarization pattern of sunlight. The atmosphere itself acts as a giant filter, polarizing sunlight in a ring around the sun, with the polarization direction pointing directly toward the sun's position, even when it is fully obscured by cloud. As a navigator slowly rotated the sunstone, the two beams of light passing through it would appear to change in brightness. The crystal would look darkest or lightest at a specific orientation, the point where its crystalline structure aligned with the polarization direction of the sky. By finding this point of alignment, the navigator could pinpoint the exact azimuth of the hidden sun, effectively drawing an invisible line straight to its location behind the clouds. This was far more than a clever party trick. It was a matter of life and death. With just a single reading, a skilled navigator could establish a baseline. But the true power was revealed by taking multiple readings throughout the day, by tracking the sun's apparent movement across the sky. Even when that sky was a solid ceiling of gray, they could establish an accurate east-west line and approximate the time of day. This allowed them to maintain a generally correct latitude, a concept the Vikings understood intuitively long before it had a formal name. They practiced what is known as latitude sailing, aiming to hit a known parallel and then running east or west along it until they made landfall. A sunstone reading, combined with their deep knowledge of wave patterns, bird behavior, and water temperature, provided the critical confirmation they needed to stay on course. It was the keystone in their entire navigational system, the one piece of data that could cut through the uncertainty and prevent a voyage from ending in disaster on some unseen lee shore. The evidence for this practice, while not yet definitive in the archaeological record, is compellingly supported by both legend and modern experimentation. A medieval Icelandic saga recounts a story where King Olaf, doubting a claim of seeing the sun on a snowy day, asked the challenger to point to it. The king then held up a sunstone, saw where the light streamed from, and verified the man's claim. Furthermore, in 2011, a team of researchers actually discovered a piece of calcite crystal aboard the wreck of an Elizabethan warship that sank in 1592, suggesting the technique, or a version of it, persisted long after the Viking Age. Modern-day sailors and scientists have replicated the method with astonishing accuracy, proving that on overcast days, a sunstone can determine the sun's position with a margin of error of just a few degrees, more than enough to guide a ship across an ocean. This was risk mitigation in its purest form. The Vikings didn't try to conquer the storm or clear the fog. They accepted the environment's challenge and found a way to see through it, harnessing a natural phenomenon invisible to the naked eye to illuminate a safe path forward. In an age before magnetic compasses were reliable in the high latitudes, this crystal was their true north, a testament to a culture whose legendary exploration was built not on brute force alone, but on a profound and observant intimacy with the hidden workings of the natural world. Now picture the heart of the Aztec Empire not on solid ground, but amidst the shimmering expanse of Lake Texcoco. The great city of Tenochtitlan was a marvel of canals and causeways, a bustling island metropolis that was home to over 200,000 people. But this aquatic paradise presented a monumental challenge. How do you feed such a dense population when your entire city is surrounded by water and your farmland is constantly threatened by flooding? The Aztec solution was a breathtaking feat of ecological engineering that turned the lake itself into their most fertile field. They created the Chinampa, often called a floating garden, though that name doesn't quite capture its true genius. These were not simply rafts that bobbed on the water. They were artificially constructed, highly productive islands engineered to thrive in an environment where conventional farming would be impossible. The construction of a Chinampa was a meticulous process that transformed the shallow lakebed into a rich, resilient agricultural platform. It began with the strategic staking out of a rectangular plot in the marshy shallows. Using long, flexible poles cut from the abundant ahujo trees that lined the lake's edge, workers would first drive sturdy posts into the soft lake bottom to mark the perimeter of the new garden. Then they wove a giant, underwater basket between these posts using reeds and other flexible aquatic vegetation. This woven cage was the secret to the Chinampa's stability and its drainage system. Into this submerged container, they began layering materials from the lake itself, each with a specific purpose. The bottom layer was often rich, nutrient-dense mud scooped from the bottom of the canals. This was topped with layers of decaying vegetation, water lilies, and other aquatic plants. The final cap was a thick layer of the most fertile material available, the rich, black, organic muck from the lakebed. This layered composition created a raised bed that was essentially a self-fertilizing, saturated sponge, with a woven reed base allowing for just the right amount of water to seep in and out, keeping the roots moist but never waterlogged. This ingenious design made the Chinampa inherently flood-resistant. During the rainy season, when the lake level would rise significantly, a conventional farm on the shore would be completely inundated and destroyed. But the Chinampa was designed to accommodate the flood. The entire garden would simply float upward, riding on the rising water, its woven foundation flexing and its rooted bed remaining perfectly intact. The crops, safely elevated on their buoyant platform, would continue to grow unharmed. As the waters receded, the Chinampa would settle gently back down to its original position. This ability to rise and fall with the hydraulic pulse of the lake turned a natural disaster into a mere seasonal fluctuation, a non-event for the farmers who tended these plots. Furthermore, the constant capillary action through the porous base of the plot drew fresh water up into the soil, while the surrounding canals provided a natural, easy-access irrigation system that required no pumps or buckets. Farmers could simply dip a pot into the canal next to their plot to water their crops. The productivity of this system was nothing short of astonishing. The constant nutrient flow from the canal water and the decomposition of the organic layers within the Chinampa bed itself created an environment so fertile that farmers could harvest up to 7 different crops in a single year. It was a perpetual motion machine of agriculture. Waste from the city, including nutrient-rich human excrement known as tequitol, was collected and used to further fertilize the gardens, closing the nutrient loop in a remarkably efficient and sustainable way. The canals between the Chinampas were not wasted space, they were teeming with life. Aztec farmers cultivated fish and waterfowl in these waterways, which provided a crucial source of protein and whose waste products further fertilized the water that nourished the crops. This integrated system of agriculture and aquaculture supported a population density that rivaled any city in the world at that time, all without the need for plows or draft animals. The Chinampas were more than just farms. They were a complete, self-sustaining ecosystem designed by humans to work in perfect harmony with a challenging environment, proving that sometimes the most powerful way to overcome a threat is not to build a wall against it, but to learn how to float gracefully above it. What ties all these breathtaking innovations together, from the dancing walls of the Incas to the floating farms of the Aztecs, is not a secret blueprint passed between empires, but something far more profound, a universal human response to necessity. These 29 engineering marvels were not conceived in isolated laboratories by lone geniuses. They were forged in the crucible of survival, each one the hard-won product of generations of careful observation, painful trial, and costly error. Civilizations did not simply live in their environments, they engaged in a continuous, intimate dialogue with them. They learned to read the subtle language of the wind, the water, and the earth, and their greatest architectural triumphs were direct answers to the questions posed by their unique and often hostile homelands. The Inca stonemason, feeling the first tremors of a quake, understood that flexibility, not brute strength, was the key to endurance. The Mesopotamian farmer, watching his levee breach, knew that to fight the river's power was futile, but to guide it was divine. This deep, localized knowledge, this place-based intelligence, is the true legacy they left behind. It was an innovation born not from abstract theory, but from the immediate, urgent pressure to protect homes, feed families, and preserve culture against the relentless forces of nature. This accumulated wisdom challenges a very modern, and perhaps arrogant, assumption that older equates to primitive. We often imagine a linear progression of technology, where our solutions are inherently superior to those of the past. But the enduring presence of these ancient structures, many still performing their original functions millennia later, forces a humbling reconsideration. While we build with steel and concrete designed to last decades, they built with stone and earth for the ages. Their perspective was fundamentally long-term and sustainable out of sheer necessity. They had no choice but to work with the materials and energy flows immediately available to them. A Roman engineer couldn't order a special chemical additive from across the empire. He had to experiment with the local volcanic ash. A Khmer water manager couldn't rely on electric pumps. He had to master the gentle, unpowered force of gravity. This constraint was their greatest teacher, leading to solutions that were not only effective but often incredibly elegant and energy efficient. They designed systems that were woven into the local ecology, like the Chinampas that created habitat or the qanats that recharged aquifers, rather than extracting from it until depletion. This is why, today, these ancient tricks are undergoing a dramatic re-evaluation. They are no longer seen as mere archaeological curiosities to be displayed in museums, but as a vast, open-source library of proven sustainable design principles. In a world grappling with the escalating crises of climate change, resource scarcity, and extreme weather events, the wisdom of the past suddenly looks remarkably futuristic. Modern engineers and architects are now looking back to these time-tested strategies for inspiration in a field increasingly known as vernacular climate adaptation. They aren't seeking to copy the past exactly, but to translate its core principles through a contemporary lens. The flexible jointing of Inca walls inspires new designs for seismic-resistant buildings that can sway with tremors. The passive cooling of Persian wind towers is being integrated into modern green buildings to drastically reduce the need for energy-intensive air conditioning. The integrated water management of the Dujongyan system offers a less ecologically disruptive alternative to massive silt-trapping dams. This revival represents a powerful paradigm shift. It moves us away from a philosophy of dominating and controlling nature with ever more complex and brittle technology, and toward one of collaborating with natural forces. It suggests that resilience in the face of disaster isn't always about building bigger seawalls or stronger barriers. Sometimes it's about designing systems that are inherently adaptive, that can bend without breaking, float without sinking, and work with the environment's rhythm rather than against it. The legacy of these 29 tricks, and countless others still waiting to be rediscovered, is a message of hope and ingenuity. It proves that human creativity, when deeply attuned to the natural world, can devise solutions that are not only powerful but also perpetual, offering us a timeless guide for building a more resilient and harmonious future. This shift from historical curiosity to active inspiration is perhaps most visible in the high Andes of Peru, where the descendants of the Inca are leading a remarkable architectural renaissance. In the city of Lima, a modern metropolis perpetually living in the shadow of the Big One, a massive earthquake predicted to devastate the region, engineers are confronting a critical problem. Modern reinforced concrete buildings, while strong, can be brittle. When subjected to the violent, twisting forces of a major seismic event, they can suffer a catastrophic failure known as pancake collapse, where floors slam down onto each other. The solution, emerging from cutting-edge seismic research, looks astonishingly familiar. Inspired by the polygonal masonry of Sacsayhuamán, contemporary architects and engineers are designing buildings that incorporate something called a seismic isolation base. This isn't a direct copy of ancient walls, but a brilliant translation of its core principle. Instead of rigidly anchoring a building to the shaking ground, these new structures are built atop a system of flexible bearings, often made of layered rubber and steel. During an earthquake, the entire building is allowed to sway and slide independently of the ground motion below, much like the individual stones in an Inca wall grate against each other. The destructive energy is dissipated as harmless kinetic movement, not concentrated into fractures. This modern application directly echoes the ancient intuition that flexibility trumps rigid resistance, proving that a thousands-year-old idea can be the foundation for the next generation of life-saving infrastructure. Meanwhile, in the parched landscapes of the American Southwest and the Middle East, the ancient Persian Kanat is experiencing a high-tech revival to address the escalating crisis of water scarcity. The fundamental challenge remains the same: how to transport water across vast, arid distances with minimal loss to the relentless sun. Modern engineers, armed with satellite imagery and ground-penetrating radar, are now designing what are essentially 21st-century qanats. They use these advanced tools to map subterranean aquifers with pinpoint accuracy, identifying the optimal paths for new underground conveyance tunnels. While the tunnels themselves might be excavated with modern machinery rather than hand-dug by mucanis, the core operating principle is identical: gravity does all the work, eliminating the enormous energy costs of powerful electric pumps. The water, shielded from evaporation in its subterranean passage, arrives cool, clean, and ready for use. This ancient technology is being hybridized with modern solar power. In some projects, small, strategically placed solar panels provide just enough energy to power sensors that monitor water flow and quality, and to run automated gates that control distribution with a precision the ancient Persians could only dream of. This fusion of timeless hydrological wisdom with contemporary monitoring systems creates a sustainable and incredibly efficient water network, turning a desert's greatest weakness, its gentle slope, into its greatest hydraulic asset. The lessons extend beyond individual techniques to an entire philosophy of design, pushing the modern construction industry toward a new paradigm of biomimicry and environmental harmony. The Roman recipe for self-healing concrete, once a lost secret, is now the subject of intense research in materials science labs worldwide. Inspired by the luminous tobermorite crystals that give Roman marine concrete its longevity, scientists are developing modern concretes embedded with bacterial spores or microcapsules filled with healing agents. When a crack forms and water seeps in, these dormant components are activated, either by the water itself or by the bacteria metabolizing nutrients, producing calcite that automatically fills the crack. This is no longer just a historical curiosity. It is the forefront of sustainable materials science, promising a future where bridges, roads, and seawalls can repair their own wear and tear, drastically reducing maintenance costs and extending lifespans by centuries. Similarly, the passive cooling strategies of the Persian wind tower and the Minoan light well are being digitally modeled and optimized for integration into large-scale commercial buildings. Architects are designing atriums that function as giant stack ventilation chimneys and facades with intricately designed channels that catch and funnel prevailing winds, all to reduce a building's reliance on fossil fuel-powered air conditioning. This isn't just about nostalgia, it's about performance. These ancient strategies offer a path to dramatically lower carbon emissions and create healthier indoor environments with a fraction of the energy expenditure. This global re-engagement with ancient engineering is more than a trend. It is a necessary correction. For over a century, our approach to the built environment has often been characterized by a brute force mentality, dominating nature with overwhelming power, abundant energy, and novel but often untested materials. The result has been infrastructure that is frequently brittle, energy-intensive, and environmentally costly. The wisdom recovered from these lost civilizations offers a different path forward, one of elegant efficiency and profound resilience. It teaches us to work with the grain of nature, not against it, to use gravity instead of fighting it, to design for flexibility rather than rigid strength. To see local materials not as limitations but as opportunities. These are not primitive ideas, they are profoundly sophisticated ones, refined through centuries of real-world testing and observation. They remind us that the most advanced solution is not always the most complex or energy-intensive one. Sometimes it is the simple, elegant, and timeless trick, waiting patiently in the ruins, for us to finally become wise enough to understand its value and humble enough to put it to use once more. From the earthquake-defying walls of the Incas to the flood-resistant cities of the Indus Valley, these 29 engineering tricks reveal a profound and timeless truth about our species, that human creativity, when deeply attuned to the natural world, can find a way to overcome even nature's most formidable challenges. These were not miracles or mere accidents of history. They were the products of meticulous observation, painful trial and error, and a willingness to learn from the environment rather than simply conquer it. Each innovation, from the self-healing Roman concrete to the gravity-fed Persian qanats, tells a story of a civilization listening to the whispers of the earth and responding not with force, but with a graceful, intelligent collaboration. They looked at a fault line and saw a reason to build flexibly. They faced a drought and learned to tap the hidden veins of the planet. They understood that true resilience isn't about building a higher wall against the storm, but about designing a boat that can rise with the flood. As we confront an era of increasing climate volatility and more frequent natural disasters, these ancient strategies offer more than just historical curiosity. They provide a vital wellspring of hope and inspiration. Our modern world often relies on complex, energy-intensive, and sometimes brittle solutions to environmental threats. We pour concrete and steel, hoping to overpower nature's forces. But the legacy of these lost civilizations presents a compelling alternative, a blueprint for sustainability and resilience that is woven into the very fabric of natural processes. They prove that longevity and strength can be achieved through elegance and adaptation, not just through sheer mass and power. The past is speaking to us, offering lessons in humility and ingenuity that are more relevant now than ever before. It reminds us that sometimes the most advanced path forward is to look backward, to rediscover the wisdom of those who learned to thrive within their environment's constraints, not in spite of them. This journey through history shows us that resilience is not a fixed state, but a continuous process of learning and adaptation. It is built on a foundation of ingenuity, on the courage to experiment, and on the profound understanding that we are a part of nature, not separate from it. The echoes of these ancient tricks can be found in the seismic base isolators of modern skyscrapers and the passive cooling systems of green architecture, proving that their genius is not lost, but simply waiting to be rediscovered and reimagined for our time. We would be wise to listen. Now we'd love to hear from you. Which of these 29 engineering marvels amazed you the most? Was it the Viking sunstone that saw through storms, or the intricate plumbing of Mohenjo-Daro? Share your thoughts and your favorite historical mystery in the comments below. And if you enjoyed this journey into the ingenious minds of the past, make sure to subscribe and hit the bell so you don't miss our next exploration into the secrets that still shape our world.